In this video, we're continuing our discussion of ordinary differential equations. And we're going to discuss the solution methods for initial value problems. In this course, we will consider several solution methods for solving initial value problems. First, we'll talk about the explicit Euler method, then the backward or implicit Euler method, Hume's method, the midpoint method, and the Runge-Kutta methods. So in this video, we're going to just talk about the first one, the explicit Euler method. So this method is also just called Euler method. So the Euler method, or explicit Euler method, is one of the simplest methods for solving first-order initial value problems. So consider the IVP as shown here. So dx by dt is equal to some function of x and t. We assume that the value of the dependent variable x, say xi, is known at an initial value ti, then we can use a Taylor approximation to estimate the value of x at t is equal to I plus 1, which would be x at t I plus 1. And here the step size h is equal to t at I plus 1 minus t at I. So x at t of I plus 1 is equal to x at I plus dx by dt evaluated at ti times our step size h plus order h squared. This is using the Taylor series expansion that we have talked about several times previously. So if we substitute our differential equation into this, so if you recall from the previous slide, our differential equation said that dx by dt is equal to a function of x and t. So if we're evaluating this at ti, then we can plug this in here. So we get f evaluated at xi and ti. So the approximation of x at some time ti plus 1, which we can call xi plus 1, can be shown as here. So x at ti plus 1 is equal to xi plus 1, which is xi plus the function evaluated at xi and ti times h. So our next estimate, or the estimate at our next time, is equal to the estimate at our current time plus the function evaluated at our current x and t times our step size h. So using this estimate, the local truncation error is proportional to the square of the step size. Because if you recall, when we looked at the Taylor expansion, we had an order h squared term following this. So the constant of proportionality of the truncation error is related to the second derivative of x, which is the first derivative of the given IVP. So our local error is order h squared. And so the errors from each interval are added together, with n is equal to L over h being the number of intervals, and L the total length, Tn minus T0. Then the total error is E, which is order h squared, times L over h, which means that our error for the explicit Euler method is order h. So it is directly proportional to the step size h, where again the step size is the difference between our time steps, ti plus 1 minus t at I. So let's look graphically at what we're doing here. So we want to solve this ordinary differential equation to give us a function x with respect to time. So what we know is some initial value ti, at our initial value ti we know xi. And we have, what we know is the rate of change of x with respect to t. So we can use this dx by dt evaluated at xi and ti to help us get our next estimate. So our next estimate is just equal to this rate multiplied by our step size h. So this is our step size h, ti plus 1 minus ti. And our next estimate is just equal to, so our old estimate plus the rate multiplied by h. So that gives us our xi plus 1. And you can see the difference between the estimate, and the actual value is this error, true error EI plus 1. So let's look at an example. If we assume that the Canadian population at some time t equals 0, which is some current year, is 35 million. If 2.5% of the population have a child in a given year, so the birth rate is 2.5%, while the death rate is 1% of the population, we want to know what is going to be the population in 50 years. And then let's look at this again. If 6% of the population have a child in a given year, so our birth rate is now 6%, and the death rate is kept at 1%, what in that case would be the population in 50 years? So the rate of growth is directly proportional to the current population with a constant of proportionality k, where k is equal to 2.025, which is the birth rate, minus 0.01, which was the death rate. So we get this net increase of 0.015, or 1.5% increase in population. So this is the constant of proportionality for our growth rate. So now if x represents the population in millions and t represents the time in years, then our initial value problem is given by dx by dt is equal to 0.015x. And we have an initial condition that x of 0 is equal to 35, which was 35 million. So we can find the exact solution for this differential equation, which is that x is equal to 35 e to the power 0.015t. If instead the birth rate was 6%, then our k is 0.06 minus 0.01, which is 0.05. Our initial value problem is dx by dt is 0.05x, and the exact solution is x is equal to 35 e to the power 0.05t. So now we want to use the Euler method to provide a numerical solution. So let's use a step size of 1 year, so h is equal to ti plus 1 minus ti, let's set that at 1. So that means each of our times is t0, t1, t2 is 0, 1, 2, up to t50 is 50 years. So we were given our initial value, x0 is equal to 35 million. So again, this is our differential equation here. So when k is equal to 0.015, the value of x1 in millions is given by using the Euler method. x1 is equal to x0 plus h times dx by dt evaluated at x0 and t0. So we take the value that we know plus the rate evaluated at the value that we know multiplied by this step size h to give us our next time, the estimate at the next time. So this is equal to 35 plus our h was 1, and this is evaluating our function at x0, so 0.015 times 35, as you can see here. So x1 is equal to 35.525. We can also write this as x1 is equal to x0 plus f evaluated at x0 and t0, where f is just this dx by dt. So now to find the next value, the value of x2 is given by x2 is equal to x1 plus h dx by dt evaluated at x1 and t1, which is equal to our value that we just calculated for x1, 35.525, plus our step size h times 0.015 times x1, 35.525. So that means our x2 is 36.0579. And this we can continue on to find the value of x at each time point. And this is implemented in MATLAB and produces the results shown here. So you can see that the exact solution is in the blue dashed line, and the Euler method with h is equal to 1 provides a very good estimate of the growth rate over time. So the approximation at 50 years is provides a good estimate of that. So the error between the exact solution to the differential equation and the numerical value at t equals 50 is given as shown here. So e is equal to 35 times e to the power 0.015 times 50. This was our exact solution. And then this was our numerical solution, 73.6835. So just evaluating this out, we can see that our true error at after 50 years is equal to 0.4 million. And the relative error in this case is 0.005. So it gives a very good approximation in this case. For the second case, when k is equal to 0.05, we can follow the same procedure to evaluate the value of x1. So in this case, again, we've got our initial condition was 35, our h is 1, and then evaluating dx by dt at x0 and t0, we have 0.05 times 35. So we find that x1 is equal to 36.75. And we can follow the same procedure and iterate further to find the values of x at each time point. So this is the output produced by the MATLAB function. And as you can see, the estimate of the population growth is not as good for with h is equal to 1 as it was in the previous case. So compared to the previous case, the error is a little bit higher. So the error between the exact solution to the differential equation and the numerical value at t equals 50 is given as shown here. So you can see when we plug in our numbers that the error is now 25.0283. And the relative error in this case is 0.06. So just comparing the two figures, you can see that the Euler method with this step size produced a better estimate for the lower population growth rate, the 2.5% birth rate. And you can also notice that the error in the Euler method increases as t increases. So as with each time step, we're getting a little bit more error introduced. You can also see that decreasing the step size can provide a better approximation. So this shows for the population with the birth rate of 6% with our h equals 1, which is what we did, as well as with h is equal to 0.1, and in this case we get very close to the exact solution. Let's look at another example, and this was taken from, or adopted from, an example similar at the link shown here. So if we have a lake that has a volume of 10,000 meters cubed, which has some initial concentration of a particular pollutant of 5 parts per billion, and the pollutant is due to some pesticide that is no longer available on the market. The volume of the lake is constant throughout the year, with the daily water flowing in and out of the lake with a rate of Q, shown here. So as the pesticide is no longer used, the concentration of the pollutant in the surrounding soil is given as this exponential decay, which we can call C in is equal to 5e to the minus 2t over 1,000. And so this indicates that this is the concentration follows in exponential decay, and this concentration can be assumed to be that of the pollutant in the fluid flowing into the lake. And then the concentration of the pollutant in the fluid flowing out of the lake is the same as the concentration in the lake. So we want to know what is the concentration of this particular pollutant in the lake after 2 years. So the first step is to properly write the differential equation that needs to be solved. So if we define a parameter alpha as the total amount of pollutant in the lake, then the rate of change of alpha with respect to time is equal to the total amount of pollutant entering the lake per day. And each day, the total amount of pollutant entering the lake is given by C in times Q. And the total amount of pollutant exiting the lake is given by C times Q, where C is the concentration of the pollutant in the lake. So basically, we have this lake. We've got the pollutant entering the lake at this rate Q, with this concentration in the surrounding soil Cn, and the amount is exiting the lake with the concentration of the lake times the flow rate, again, Q. So we can write this differential equation that d alpha by dt, or the change in amount of pollutant with respect to time, is equal to our flow rate times the difference between Cn and C. So the concentration is equal to the total amount divided by the volume. So if our total amount was alpha, the concentration is just going to be alpha divided by 10,000. So here the change in concentration with time is equal to this divided by 1,000, or divided by 10,000. So this means, so this is the form of our differential equation that we need to solve. So here we've plugged in the form that we know for Cn in here. So now we have this equation that describes the change of C with respect to time. And it is a function of both time as well as C. So finding the exact solution to this differential equation is not an easy task, so a numerical solution would be the preferred route in this case. So let's take a step size of 1, so Ti plus 1 minus Ti is equal to 1, T0 is equal to 0, and our initial concentration C0 was 5 parts per billion. And we want to use the Euler method to find the concentration C at T is equal to 730 days, or 2 years. So just showing the calculations for the first two estimates, C1 and C2. So T1 is 1 day, or C is equal to, or C1 is equal to C naught plus H dC by dt, evaluated at C naught and T naught, which can also be written as shown here. So plugging in the form of the differential equation, as well as T is equal to 0 here, and C naught is equal to 5, which was here, we find that C1 is also equal to 5. Then at 2 days, C2 is equal to C1 plus H dC by dt, evaluated at C1 and T1. So again, plugging in the form of our differential equation, and now here we've got T is equal to 1, and C1 again was equal to 5. So we find that C2 is equal to 4.9999. And carrying on, we find that the concentration in the lake at T equals 730 days is about 1.4238 parts per billion. And this shows the MATLAB output with the concentration of the pollutant in the lake over time. So let's consider one more example. And in this example, we're going to investigate the issue of stability of the numerical solution of differential equations using the Euler method. So consider initial value problem of the form shown here. So dx by dt is equal to minus x. If x naught equals 1, we want to compare two solutions taking step sizes of first h is equal to 0.1 and then h is equal to 3. So the exact solution of this ODE is that x is equal to e to the power minus t. Using the explicit Euler scheme, the value of xi plus 1 can be obtained as shown here. So xi plus 1 is equal to xi plus h dx by dt, x evaluated at xi. So if we plug in the form of our dx by dt here, evaluate this at xi, so we have xi plus h times minus xi, which is equal to 1 minus h times xi. And if we write this for xi and relate that to xi minus 1, then xi is equal to 1 minus h times xi minus 1. So basically every time we have the next time step is equal to 1 minus h times the x at the previous time step. So this means we can plug this in to here. So xi plus 1 is equal to 1 minus h times 1 minus h xi minus 1. So we can write this generally as xi plus 1 is equal to 1 minus h to the power I plus 1 times x naught, relating x at any time step I plus 1 to the initial condition x0. So when h is equal to 0.1, then this term 1 minus h to the power I plus 1 is equal to 0.9 to the power I plus 1. And this is bounded for any value of I, which means that the value of xi plus 1 is always bounded. However, if h is equal to 3, then this term 1 minus h to the power I plus 1 is equal to negative 2 to the power I plus 1, which oscillates wildly, leading to an instability in the numerical scheme. So these figures show or illustrate the solution for different values of h for this problem. So using h is equal to 0.5, you can see that although in this case it does not provide a great approximation in this area, at least the solution stays bounded. It does not behave wildly. If we start to increase h, so here h is equal to 0.5, we start to get this oscillatory behavior in our solution. When h is equal to 0.2, you can see that we're just bouncing back and forth, or when h is equal to 2, we're just bouncing back and forth wildly over the actual solution. And then when h is equal to 3, in this case, we get this really quick divergence of the method. So this just illustrates the stability of the explicit Euler scheme, and how sometimes if you have a step size that is too large, the method can become unstable.